Hello, my name is Hugo, and today I'm going to talk about why we need kernel interposition over the network data plane. Okay, so most of you are probably familiar with how a traditional kernel network stack works. In this model, the kernel sits between the NIC and applications and is responsible for mediating all the data transfers to the network. And while this model worked really well for many decades, in the last 10 years or so, we saw NIC speeds growing significantly while CPU performance started to plateau. And as a result, the kernel became a bottleneck to many networked applications. And the reason the kernel performs poorly is that it has to introduce overhead due to data movement. So it needs to copy data between the kernel space and user space, and it also has overhead due to system calls. So as a response, there have been many proposals that advocate for a kernel-bypass network stack. And in this model, you let applications interface directly with the NIC without going through the kernel. So now because you're avoiding this additional data movement, you are able to achieve much better performance. The problem is that kernel bypass also leads to maintenance and manageability nightmare for administrators. And this nightmare really stems from the kernel bypass's inability to fully replicate kernel functionality. And to illustrate why this is the case, I'm going to show an example using Alice, who is a system administrator, and Bob, who is a newly hired intern. Okay, so Bob is actually quite happy. He just deployed his first application to production. The problem is that soon after, Bob realizes that his application is sending too much traffic, not leaving enough bandwidth for the database. Well, Alice knows what she needs to do. All she needs to do is prioritize traffic from the database over traffic from Bob's application. And for that, she can use tools like DC to set queuing disciplines in the kernel. And since the kernel can oversee all the traffic, it is able to impose arbitrary policy. But writing a very inefficient application wasn't the only mistake that Bob made. He also set a weak password, and that caused the server to be compromised with a malicious web server. And again, Alice knows what she has to do. She only needs to find which application is listening on port 80, and for that she can rely on the kernel's knowledge of all the open sockets in the system, and use tools like nextStat or SS to find which process is listening on port 80. And these are only two examples of the many policies and debugging capabilities that were made possible by the kernel's ability to interpose in other traffic. Now, if we move to a kernel bypass strategy, we no longer have kernel interposition, and it's no longer possible to enforce these policies or have centralized debugging capabilities. And there are existing alternatives that look at how to bring interposition back to kernel bypass. So for example, Google uses a system called Snap, which implements the network stack as a separate process running in a different core. And because it forces traffic from all applications to go through Snap, it is able to implement some of these policies we saw that are usually implemented inside the kernel. The problem is that when it does that, it also has to reintroduce data movement overhead, because now data has to hop between different cores before going out or before reaching the application. Another alternative is Microsoft's XONet. And what XONet does is to move a virtual switch to the NIC. And again, because this virtual switch can interpose between applications in the network, it can also implement some policies. The problem is that XONet, in the XONet, the control lies with the hypervisor. So it has no visibility into the applications running inside virtual machines. So many of the policies we want to implement actually require visibility into applications. So like in the example I gave, where we want to prioritize traffic from one application with the other, we need to know from which application the traffic is coming from. Or if you want to know which sockets are open, we also need to have access to the kernel's data structure with the open sockets. Okay, so what do we really want? We want something that is logically like the Kernel Network Stack, while also being physically like Kernel-Bypass. So we want to have kernel interposition without reintroducing these data movement overheads. So we want something that is on-path. And our proposal to this is this new OS architecture that we call KOPI. And KOPI stands for Kernel On-Path Interposition. And the idea is quite simple. We leverage programmable SmartNiCs to implement a network data plane that is both on-path while also being logically controlled by the kernel. And here's what it means more concretely. We're going to use a SmartNIC in a CPU, and on the CPU we have the kernel, which acts as a control plane. And the kernel is also responsible for defining the data plane functionality that runs in the SmartNIC. So for that, the kernel can actually install code on the NIC to define the data plane functionality. And that is in contrast with the traditional offload approach, where these offloads are defined by hardware vendors and not the kernel. And the reason this is essential is that data plane functionality changes often. So for instance, in Linux, over the last year alone, we saw hundreds of new commits on network filters and on network schedulers. And now applications can talk directly with the kernel for control plane operations and with the KOPI data plane for data plane operations. So right now we are developing a new operating system that we call Norman that implements a KOPI data plane. And Norman really has two main pieces. First, it has a KOPI data plane that runs on an FPGA SmartNIC, and that is responsible for all the data plane functionality that requires interposition. So things like filters, queuing disciplines, packet sniffing, and others. And now the library is responsible for all the remaining data plane functionality that does not require interposition. And then the kernel itself, which is based on Linux, is responsible for all the control plane operations. So things like connection establishment and termination, policy configurations, and defining the data plane functionality. So now, if you want to use it like tools like IP tables to set a filtering rule, we're going to use that tool as we usually do with Linux. But now the kernel not only sets its own data structures, but it's also responsible for configuring this rule in the KOPI data plane. And the same for other policy configuration tools like DC. And now, if the application wants to open a new connection, you can do so by calling connect. And since this is a control plane operation, the library can direct that to the kernel. And then the kernel is responsible for configuring this new connection in the KOPI data plane. Once this connection is established, the application can go write, and then the library will direct this data directly to the KOPI data plane. Okay, so this was Norman in a nutshell. And before I conclude, I'd like to highlight only two of the many challenges we still need to address. First, recall that Norman needs to keep per connection state on the NIC. And since the SmartNIC devices often have limited memory, it's unclear if you can scale this design to support enough connections. Another challenge is how we actually make an FPGA reconfigurable enough for our purpose. Because we must be able not only to change configuration runtime, but also functionality. Alright, so to conclude, I hope that I have convinced you that kernel interposition is essential. And the KOPI architecture really gives a path to restore kernel interposition without reintroducing overheads. And with that, I thank you, and I can take any questions.